It was Mr. Anderson, Mr. Signal Corner, and I was scream about it.
Hi, everybody. A plan here for today is to talk about the next two sections that will be on the next test, not the ones coming next class. Before I get into that stuff, though, is there any last minute things that we need to talk about? Everybody's okay with the test format? We've talked about that a couple of times and kind of what to expect. What are the, like, I must have this thing, like, at least memorized enough that I'm able to use it functionally. I talked about, like, the things that would be good things to review from. If you guys don't have anything this minute, you can always come back and find me some CT, as you assume there's some studying that's going to happen tonight, and you may be changing your mind tomorrow, and you can always come back and find me, no big deal. Fourth hour? Yes. Second hour is my prep.
Okay.
And then I have community time. I know student council is probably busy always.
Yeah. Actually,
Homecoming stuff, but
yeah.
Actually, yeah, that's probably right. Yeah, that's pretty true. Lucia.
Can I come in tomorrow during CT to do that quiz?
Yeah, for sure.
Okay. Because I was going to do it today, but it was there.
Yeah, I totally understand. No problem. All right. So let's kind of start here. So this is what we're going to do here today. We're going to begin. It's the beginnings of calculus. So a little story about, like, historically where the beginning of calculus is. So the person largely credited with the creation of what we call calculus is Isaac Newton. He was a student at, I don't remember if it's King's College or Trinity College or Cambridge. It was one of the universities in London in like the 1700s. Plague hits London. Everybody gets quarantined. He sends home back to the country outside of London. Go on for about a year. In that, when he returns, he has gravity worked out as an appendix to his work on gravity. It's the foundations of calculus. Also comes back optics, how light works, all worked out. Probably the most productive year in science in the history of humanity. He did this by himself, alone, at his house. Because he didn't have anything else better to do, I guess. So calculus is really was created as a tool for Newton to really answer a specific question, right? The question he wanted to answer was, I take an object, I drop it. How fast is that object going at some instant? Right? I can calculate the average velocity, the average rate of change, which you guys talk about in AP pre-calc last year, right? Average rates of change, which is really just a fancy way of saying slope, right? And I can calculate the average velocity of a falling object by just measuring how far the thing fell and the amount of time it took to do it, right? Distance divided by time. But if I want to know how fast is it moving at that one instant before it hits the ground, or anywhere along the path, to do that I kind of need to figure out the slope, that rate of change, with just one point. And that's the workaround that calculus is kind of designed to get around. Is how do I do this if I only have, like I'm calculating the slope of something, but just with 1 point instead of 2. Is everybody kind of okay with that? So in 2.1, we're really just talking about average rates of change. So the goal, when I say average rate of change, you think slope. So average velocity is slope. Average whatever is slope. Okay? That's all it is. So we're going to do a little bit of vocab to build out to what we're going to be calling our first main calculus idea, which is the derivative that'll come up here today. So we're going to start with this idea of a tangent. So in geometry, we defined a tangent as a geometric object. It's a line that intersects a circle at exactly one point. So like this little pink line here is a tangent, right? Hits that circle in exactly one place. Newton said, okay, well, that tangent line has a slope. What if I want to find a tangent line instead of to a circle, but to like a curve? Right? So the definition needs to be a little bit different, right? Because that tangent line could intersect the curve more than once, right? But, you know, like I can find a small enough neighborhood where that tangent line is only intersecting the curve once, right? Like if I look at a small enough neighborhood, you know, tangent to it at that point. Everybody's okay? So how am I going to, and what I eventually want is that the slope of that line, right? The slope of that tangent. That's what I'm going to be looking for. So I have a point for that tangent line. But if I want to get a slope, I don't know what the slope of that tangent line needs to be. So I can't just pick another point on T. All I have is this P, the point on the curve that I'm trying to draw the tangent, you know, something that's tangent to the line, or tangent to the curve with. So how am I going to do that? Well, here's his idea. He said, well, what if I just start with a secant? So in geometry, the definition of a secant line is a line that intersects a circle twice, right? So here's a secant. And he says, well, what if I notice that, like, if I fix, say, this point A, and I just let this B move closer and closer and closer to A, what eventually I start to get is something that resembles my tangent line, right? Is everybody okay with that? So if I can find that, if I take that B to be infinitely close to A, that should basically give me the tangent. Everybody's okay with that? And as long as those two aren't precisely equal, I can do a slope to find that. I can just do a slope calculation to get the slope of my tangent line. Okay? What does this sound like we're doing? It should sound like a limit, right? As we're getting infinitely close to something, but not actually getting there. Sounds like a limit. I know that it's the first time you're seeing a limit, like outside of just like this limit problem. What does this really mean? But that's what we're talking about, right? Is we're looking at the limit as B approaches A. Everybody feels okay with what I'm describing? So let's try an exercise now while we do this with an actual curve, and we kind of do the same thing that we're describing here. So we have the pink line, that's the tangent, that's what we want. And then I have a blue line, that's our secant, that's what we're going to start with. And we're looking at the curve y equals x squared. And the point on that curve that we want to find the tangent line to is the point 1, 1. Pretty okay there. So we're going to start first by calculating the slope of PQ. So really, if this is like x comma f of x, and this would be like 1 comma f of 1. What am I looking at here? I'm looking at a slope calculation, right? Is everybody okay with that?
Is that right? Not the slope of like a non-linear line, like a parabola. That is.
We're getting close.
Okay.
We're getting close to it. In pre-calculus last year, did you have a special name for this fraction? Call it difference quotient. Does that vocab sound familiar? Yes? I just want to try to connect this to ideas, things that are familiar. I don't need you to use the vocab if you're not familiar with it. I'm just hoping that, like, oh yeah, we did that. We talked about difference quotients. Just slope is all it is. I'm just trying to, connect it together. Okay. So if I take some specific point Q now, instead of the point Q being this general x comma x squared, let's pick some specific point on that parabola. So I picked the point 1.5 comma 2.25. Now, how did I get the 2.25 part? Just 1.5 squared, right? I just took the 1.5, plugged it into x squared, right? That'll give me the y coordinate. So here's this. What if I take Q to be a little bit closer? What if I pick it to be 1.1? So the y there is going to be 1.21, right? So I get 2.1. And as I let that Q get closer and closer to the point 1,1, that slope is going to get closer and closer to the slope of the tangent, right? This should feel just like what we're doing is doing a table to evaluate a limit, right? That's all we're doing. Does that look familiar? Does it feel kind of the same? Now, it's a little bit like more effort to get there, but if you were to take a guess, what does it look like this slope is approaching? Looks like it's probably heading to 2, right? And we would do the same thing, building on a table till we get a feel for the pattern and make a guess. That's essentially what the homework in 2.1 is going to feel like. It's just like approximating a limit with a table. They won't say the limit.
It's 1.1 and 1.1, just like random numbers you picked.
1.21 is 1.1 squared.
Oh.
So I'm just plugging it in because my function is y equals x squared.
Okay.
So I'm just getting closer and closer to the 0.11. So I had 1.5, then I have 1.1, and I can pick like 1.01.
And I'm just curious, for the one image above, like the T is L tangent to curve C, was it tangent or is that above more? Above that one too? Because like it hits it at P, but it goes through twice, so it's not.
Right. So this is a tangent. It's just tangent to the curve at this point.
Okay.
So in the neighborhood of that point, it's intersecting at once.
Okay.
That's what we mean. That it's real rare for us to be able to draw a tangent line that only intersect the curve at exactly one point. Like if you have a parabola or something like that, it's doable. But if it's like, probably not going to work out.
So if it gives us the table, we don't have to square the x by the y, we just use the y that's given.
Yeah.
Right? Okay.
Yeah.
And we
Or-
still use the same formula?
And well, it's not, it depends on what the function is that you're looking at.
It's not telling us the function, it just
Right, so if all you have are y's, then
Yeah.
there's nothing to do, right? You just calculate the slope each successive time and take guesses what the slope of the tangent line is by looking at the secants, right? So PQ is my secant, right? So that's like a secant, that's a secant. And then for the tangent, we would guess it's about 2, based on what we're seeing with the secants getting closer and closer and closer. Does that make sense? From a vocabulary standpoint.
Yeah, I think so, yeah.
So all you're doing is just doing slope over.
And we're still using the same formula that PQ just to find it.
The slope formula will be done the same. It's always going to be
Okay.
y2 minus y1 over x2 minus x1.
Okay.
Always. Nothing funny is happening with slope. Slope stays slope. So the big idea is we can find the slope of the tangent line by just looking at the limit as q approaches p of that difference quotient. So in this case, that, or I can just look at the x value, right, where the limit as x approaches 1 of like f of x minus f of 1 over x minus 1. Make it a little bit more general, so it's not specific to x. Now, what did we say that limit was? It looked like 2, right? That's what we observed above. So if I want to write the equation for that tangent line, I have a slope, 2, and a point, 1, 1. To write the equation for that line, I would use the point slope equation. So I have y minus 1 equals 2 times x minus 1. That's a perfectly legitimate equation for a line. If the directions asked for the equation in slope-intercept form or standard form or whatever, you might have to do some rearranging, but like, I hope that we're comfortable enough with our algebra skills to rearrange this into one of the other things, right? That's not too bad. So again, vocab, average rate of change, slope of the secant line. Instantaneous rate of change, that's the slope of the tangent line. In 2.1, you'll approximate that by looking at successively secant lines that are getting closer and closer and closer to the actual point. And I have 4 problems for you to try. Everybody's okay?
Yeah.
Okay, we're going to jump to 2.7. Now that we have our limit tools that we built up over the previous, 4 sections, we're going to pick up where we left off, right? We can calculate the slope of a secant line, right? That's all this is from our picture, right? PQ is a secant. So far, so good. And as we move that point Q closer and closer to P, that secant line is getting closer and closer to being the tangent line. It's okay with that idea. So what we'll do is we'll define the slope of our tangent line to the curve y equals f of x at the point P, which is a comma f of a, as the limit as x approaches a of f of x minus f of a over x minus a. So that's all that's happening. So we have the point a comma f of a. We have some point, and the x coordinate of that point is getting closer and closer and closer and closer to a. Right? That's what that limit is saying. Alternatively, we can look at the limit written this way. It means the same thing. The limit as h approaches 0 of f of a plus h minus f of a all over h. So to just kind of give you a feel for like what we're saying here, I'm just going to draw this same example before. We'll just call this f of a. And this guy is going to be just some h further down the road, right? Okay with that? Where h is just the difference between the point we're looking for the tangent at and this other point. So if I look at the slope here, the limit as h is going to 0, as this point, as this point moves to there, right? If h goes to 0, a plus h becomes a, right? Of f of a plus h minus f of a over a plus h. I'm sorry, a plus h minus a. So again, same thing, right? It's just slope. It's just written a different way. Why give us both of them, Mr. Like, why do both? For the most part, it won't matter which way you write it. In some specific instances, one of them may make the algebra more convenient than another. That'll be later, but we see that kind of thing happening. But that's all. They mean the same thing. You could use them interchangeably. The only reason you might give one preference over the other is it might be easier algebraically to handle than the other. Everybody's okay? For the most part, we use this. This one tends to be the easier one. But not always. But probably. Okay? So again, this is basically the picture that I just drew. Let's do this now in practice. Notice this is the same problem from before. We're going to actually find the slope of the tangent line now using that procedure we've just outlined. So it doesn't matter which version of that tangent line calculation we're going to do. So just for grins, we're going to do this twice. I'm going to do one using the first definition and the next example using the other definition, just to give you a feel for how each of them works. Is that okay? So my slope should be the limit as x approaches, this is a, and this is f of a, right? And then we have x, comma, f of x, so that's just x squared, right? So it's going to be f of x minus f of a over x minus a. That's my formula that I'm filling in. Oops. I guess I'll write. So that's the limit as x approaches 1 of x squared minus 1 over x minus 1. Everybody's good with the filling in that I did? Notice how I tried direct substitution here. What am I going to get? 0 over 0, right? That's one of those indeterminate forms. So that direct substitution is not going to get me there. What should I do to clear that indeterminate form?
It's an x squared minus
Factor and reduce, right? Yeah. X squared minus 1 factors to x minus 1 and x plus 1. So I can just reduce those out of there. And now I can direct substitute. And I get that the tangent, slope of the tangent line is 2.
What's the thing x squared. In the directions.
X comma f of x,
Yeah.
and then I wrote that the f of x is x squared. So I'm just kind of trying to put it in the notation that I'm using here, so that you can see how I filled this formula in. Right? F of x is my x squared. Just try to. Is that okay? All right. Let's do the same thing. We'll use the other notation now. So the other version of the limit form, or the slope formula. So here it's going to be the limit as h approaches 0 of f of a plus h minus f of a all over h. Hi, Anthony. So here's my a, and here's my f of a. And then I have like an x comma f of x over here, where the f of x is that 3 over x. Does everybody feel okay? All right. So f of a plus h means I'm going to be plugging a plus h into f of x. Right? So that means f of a plus h is going to be 3 over a plus h, right? I plugged a plus h into f of x. So plugged it into 3 over x. Good to go? Okay. F of a is going to be, well, my a is 3. So if I plug that in, I get 3 over 3, or just 1. I'm going to write it as 3 over 3. So when you go back and look at the notes, it's a little bit clearer as to where the 1 comes from. Good. Now I'm going to do that. Is that okay? I feel like going back and looking at it, that's a little clearer than if I just wrote a 1 there. Yeah. Absolutely. All right. If I plug 0 in for h, what am I going to get? If I try direct substitution here, plug 0 in for h. 0 over 0, indeterminate form. Oh no! Well, we can't do that. How are we going to clear that indeterminate hurdle? I'm not going to use a conjugate. There's no square root here. What I want to do is simplify that complex fraction, right? I have a fraction inside of a fraction. The easiest way to do that is to multiply by the least common multiple of the denominators. So my denominators are a plus h, 1 and then 1, right? 1 is 1 over 1, h is h over 1. So the least common multiple of a plus h, 1 and 1 is just a plus h. So I'm going to multiply the top and bottom of this by a plus h. Okay? So that a plus h is going to distribute to both places. What is 3 over a plus h times a plus h? 3. Excellent. And what is 1 times a plus h? A plus h. And what is really, I guess, what is a here? A is 3, right? Sorry.
Would it be negative?
Because I should have written it. I should have written this as 3 plus h also. My apologies, guys. I should have done that.
And then it would be negative 3 minus.
Yeah, I'm going to write it with the parenthesis there, and then we'll distribute the parenthesis through. Everybody's good? Mr. Kulik, why didn't you FOIL out the denominator? Because I'm hoping at some point to be able to reduce this fraction, which requires the denominator being a factored form anyway. Whenever I do this, I am not multiplying the denominators out unless there's like more than one term down there already. right? There's no like terms to combine by doing the foiling the thing through, not multiplying. In the denominator. Numerator, yes. But, okay, as Brooks had suggested, that negative sign does need to distribute through. So the 3's cancel, right? And then you notice that I have negative h over h times 3 plus h. H is canceled, right? So I'm left with the limit as h approaches 0 of negative 1 over 3 plus h. Okay? And now if I do a direct substitution, is everything okay?
Yeah.
Yeah, it is. I get negative 1/3. And there's my slope. Everybody feel okay? Again, you could have done either method for either of those problems. There's probably no, there's nothing to be gained doing it one way or the other. These ones are pretty easy to grind your way through either of them. So just to kind of remind ourselves, so average, and then in physics we talk about velocity often as our rate, but really any average, I should say rate, is just going to be unit divided by time, right? And maybe I'll say quantity here. So our instantaneous rate is just going to be, for instantaneous velocity, is just going to be our slope of our tangent line at the specific value A. All right, so let's do a physics example problem. Any physics students in the house here? A couple of us, that's great. You're like, I'm not a physics student. Am I at a severe disadvantage here? No. The physics students will just get a nice little bonus, because this will start overlapping with the stuff they're doing. They'll be like, oh, that's such an easier way of doing this physics problem. It's just use some calculus rather than doing all these algebraic methods, memorizing all these formulas. I can just kind of create my own formulas. See, it's like that doesn't sound helpful to me, but okay. I'll not say anything now, but I'm dubious. All right, so here's our example. It says, suppose that a ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. What is the velocity of the ball after 5 seconds? How fast is the ball traveling when it hits the ground? So notice none of these are average velocities, right? It's asking for some velocity at a specific time, either at 5 seconds or some unknown time, but where we know the position, where the ball's right about to hit the ground. So these are both instantaneous velocity questions. They're both going to be talking about the slope of a tangent line to a curve. What's the issue here? What aren't we given in this problem that we've been given in the previous examples? Well, we don't have the equation for the curve, right? Everybody agree? Now, our textbook is assuming that you guys know physics and know the equations for motion. I wouldn't make that assumption of you. I would give it to you on a test or quiz setting if I asked you a question like this. So the position function that we're going to be using (4.9 t squared). So S in physics talk is your canonical letter for position, V for velocity, A for acceleration. Don't ask me why S for position. I don't know why we did S. Not a physicist. I can do the math. I don't know the physics. So what I have here is like t comma 4.9 t squared, right? So in part A, we're asked for v of 5. So that's going to be using this formula up here, the limit as h approaches 0 of s of 5 plus h minus s of 5 over h. Does everybody feel okay here? So if I go ahead and plug stuff in, I'm going to have 4.9 times 5 plus h squared minus 4.9 times 5 squared over h. This is like t comma s of t, right? So s of 5 plus h is plugging 5 plus h in for t. So you got a mouth open and like, oh, I don't know, are you okay? All right. Okay, that's fine. I'm just checking. We're doing okay? So what am I going to do next? If I try to do a direct substitution, what's going to happen?
0.
Indeterminate form. Yep. So what should I do?
Maybe we should.
Not factor. What's the other F word? Foil, right? Foil this stuff out.
That's what I was.
So I'm going to do that in my head, but I'm not going to do it all the way. Uh-oh. I did something wrong. Who sees what I did wrong? I wrote down something wrong here. Who sees the mistake?
Where did h go? Like the squared. I don't know.
Who sees it? Maybe I should say I forgot to write something down.
No, he did that. It says the squared over the h.
Limit, right? On your test, if you forget to do that, am I going to mark down?
Yeah.
Yes. Okay. So on all these limit problems, again, got to be careful. See how easy it is. I did it. Now I noticed I did it right away. Almost like I did it on purpose when you weren't expecting it to check to see if you were going to catch it for me. That's okay that you didn't. This is me reminding you that you need to be careful about this when you do it by demonstrating how easy it is to get carried away and forget it. So when I FOIL this out, I have like 5 squared plus 2 times, there should be a 5 in here also, times 5 times h plus h squared, right? That's me FOILing that out.
Yeah.
Yeah, kind of, sure. So, bloop, bloop. Those guys can both go, right? Oh, if somebody complaining that this was missing, yeah, that I should have listened, because that's correct.
What are you foiling?
5 plus h squared,
Oh,
right?
gotcha. So is the 2 times 4.9h, could that just be 10 times 4.9h?
Yeah, 2 times 5 times 4.9h. Yeah, or 49h. Right.
Oh, that makes sense.
So, notice everything that's left all has h's in it, right? Let's reduce. Bloop, bloop, bloop. Got 49 plus 4.9h. And then you just plug the 0 in.
Pull the H out, or can you just get rid of it altogether?
Yeah, I mean, you can think about it as like, and like reduce.
Okay.
Either way though, like when it's stuff like this, I don't want to add an extra step personally. Like I see it, everything's got an H, I just take an H out of everything. It's doing the same thing as factoring the H out and then reducing. So either way of showing your work is fine with me. Right, like, is everybody okay? This guy should have a unit though to it, right? I think we're in meters per second. So 450 meters times in seconds, so velocity is meters per second. Yes. Of course. Yeah, go ahead. Do you feel okay doing that? It got a little messy, right? I have some good news for you coming soon.
Really?
Yeah, this gets easier
Yay.
in like 2 sections. Like 2 more sections, and it's going to get way easier to do these things. In fact, the rest of, like the next chapter and a half is going to be devoted to, like, how do I do this easier without having to do the limits? Yeah, right? Like, it's coming. You just got to bear with it for, like, 2 sections, and then we, like, make it easier to do it. All right. So here it goes. This thing. Oh, yeah, we didn't do B. All right, sure. It says, how fast is the ball traveling when it hits the ground? What we need there is a time so that we're able to do this, right? We got to find the time, and then we'll do the same thing with that time, right? So what is the position that ball needs to be? It has to have traveled 450, right? Everybody's okay? So T should be the square root of 450 divided by 4.9. I'm actually going to change the color on this because I'm going to be real lazy on the next step. I'm writing the same thing. I'm just going to write it in green because I'm seeing what's in my future and I don't like it. Yeah, do you ever look at that and go, oh, this is just going to be like so tedious about to do? Like, I wish there's an easy way to do it. Yeah, this is what I'm going to do right now. So this is my T, right? Yeah, so it would be plus or minus, but we're talking about time.
Oh.
So we can drop the minus because negative time, what the heck does that mean? What we got here? We're something going to do some time travel. So all this is going to be then the exact same work, but instead of 5, I'm going to have this stupid square root in here. So everywhere there was a 5, I'm going to pick up that square root. So this piece then would just become 2 times square root 450 over 4.9 times 4.9. So the 5 is just this time, right? This was at 5 seconds. We're doing the same limit, just now it's this gross looking radical seconds. So the work is going to be identical, right? Just everywhere there's a 5, I'm going to have this radical. right? So that all gets just replaced. And now to here, maybe we'll just do yeah. Okay. All right, so I still have blue. So that one. And now let's change color. This guy now is 2 times square root 450 over 4.9 times 4.9. Because I've just taken those two guys. So this is just me like not wanting to write all the work out again and showing you that it's going to be the exact same process, just with a different number in there. That's all I do. So it's the exact same algebra, the exact same work. There's just a different number in place of the A. Does it change the result at all? I mean, the number at the end is different, but all the algebra is the same. I take advantage of that. And that's the next section. But this is a good preload for that. Look at how easy that was. It's almost like, could I just do this arbitrarily from an arbitrary value and find like a function that'll just, I can plug in A's and spit out slopes. Almost feels like I should be able to do that. That's the next idea in the next section. If you're like, what the heck are you talking about? We'll get to it in the next one. Don't worry. We'll see it again. I will say it again. You'll understand it better when I do it again. I'm just previewing it. So, definition. We say the derivative of a function f at the value a, which we denote f prime of a, is equal to that slope of the tangent line, right? Which is the same thing as, so f prime of a is the same thing as the limit as x approaches a of f of a plus h minus f of a all over h, which is also equal to the slope of the tangent line to f of x at x equals a, which is also equal to the instantaneous rate of change of f of x at x equals a. They're all saying the same thing. Don't you love when we have 4 different ways to say the same thing? Oh, no, I hate that. But that's what's going on here. And why don't we make it 5? Because you could also say it that way. Is this okay? So just do like a vocab thing here. That all these sets of symbols, these phrases mean the same thing. Is it important that you know this? Vitally important. The AP is going to ask you to do the same thing like 100 different ways, where it's like, you're really asking me to do the same thing again? Okay. But what they're doing is they're testing to make sure you understand the vocab. Yeah. So, yes, this is critically important. You'll see it over and over and over and over. And over 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 again. Here, it's asking us to find the derivative for this function f of x at the number a. So the symbol we use for that, f prime of a. Of course. Which we know is the limit as h approaches 0 of f of a plus h minus f of a all over h. Or you could write it the other way. I'm choosing to use this one because it's Brooks.
So, I know you've been talking about it, but I've heard like before, like calculus things. I don't really know, but like, what exactly is a derivative?
The instantaneous rate of change for a function. So it's the slope of the tangent line to the function at that value x. So it's essentially the slope at a point. Instead of the slope between 2 points, slope at a point.
Slope at a point. Tangent.
Yep.
Okay.
Slope of the tangent line. Same thing. All saying the same thing. Yep. All right. So we have this, right? So this is my f of x. So f of a plus h means I'm going to plug a plus h in for my x's. And then minus f of a. So I'm going to plug a in for my x's. What I did there. Okay. Let's FOIL this guy out. Let's distribute this through and distribute that negative through. And yuckarooskies, Mr. Kulik, this is getting pretty gross. Well, here's where the good stuff starts happening. Let's look. I have a positive a squared and a negative a squared. Boop. I have a negative 8a and a positive 8a. Boop. I have a positive 9 and a negative 9. Boop. Look at the stuff that's left. You notice that it all has something in common? They all have h's. Guess what I can do? Reduce those h's. So I have the limit as h goes to 0 of 2a plus h minus 8. And if I direct substitute, I have 2a minus h, or sorry, minus 8. Guess what I can do with that then? If I want specific values of a, do I have to go through that rigmarole that I just did again? Just plug it into 2a minus h, right? If I want to know the slope of the tangent line to that curve f of x when x is equal to 5, just plug 5 into a. If I want when x is equal to 10, plug it into a. So the idea is let's do this once. And this is like a slope function now that spits out the slope of the tangent lines for a given x. And now I can save myself having to do that whole rigmarole every single time. That's what we're hinting at above. We'll formalize that idea more in 2.8, where we talk about the derivative as a function. That's kind of what we're getting towards. But we're not ready to do that yet. Tangent line to the curve at A is the same thing as the derivative to the curve at A. That's the same definition that we wrote it before, right? Yes, sir. If I want to find the equation of the tangent line to this parabola at the point 3, 6, so I know the slope of the tangent line is just f prime of a, which is 2a minus 8. We did that in the previous example, right? So my slope at 3, -6 is just 2 times 3 minus 8, -2. Woo! Look at how easy that was. Did I have to do a limit there? No, man, because if I have a big complicated problem where I'm asking about derivatives for some function, I'm just going to do it that general way and then use that as a slope function to plug stuff into. Yes? The derivative of f of x at a, which is what we calculated right back here. Right? But we did all this googly-gog to get 2a minus 8.
So example 4 and 5 are the
Yeah, I'm just saving myself the work. Yeah. So, then I can write my equation, my tangent line. So, y minus y1 equals m times x minus x1. And I'm done. Right? Unless they ask for some specific form for my answer to be in, that is an acceptable stopping point. This, the instantaneous rate of change. That's just the definition that I said, like, hey, all these 3 different ways, or 5 different ways of saying this all mean the same thing. This is one of them. This is just included right up here, right? Where I just linked all these things that they all mean the same thing. Yeah. So that's all that's saying. Same thing here, just connecting it all together. Let's look at this example. I think this will be the last thing that I need to look at here. Sound good? It says a manufacturer produces bolts of fabric with a fixed width. You know what bolts of fabric is? It's like you take a sheet, you twist it up onto like a roll. If you've ever been to like Joann Fabrics or something, they have like, they take the things out and they unroll the fabric from it. That's a bolt of fabric. Yeah. Anyway, the ladies in the room are like, yeah, I know that. The boys in the room are like, what's Joann Fabric? Maybe you went there with your mom or something. No. It doesn't exist anymore. They did all close.
Yeah.
I know. Where am I going to go get my bolts of fabric now? Probably Hobby Lobby has that covered. But they're not open on Sunday, which is a bummer. I know these things because my wife is a crafty lady. And I've taken many trips to these places and been discouraged that Hobby Lobby wasn't open on Sunday. Anyway, back to the problem. The cost of producing X yards of this fabric is C equals f of X dollars. What is the meaning of the derivative f prime of X? What are the units? So, what I need to think about is my y coordinate and my x coordinate for my function c is x comma c, right? X is in yards and c is in dollars, right? So, let's do the unit first. The unit will just be, if it's really just slope that we're talking about, instantaneous slope, it's going to be the y unit per the x unit. Dollars per yard. Is okay. So f prime of x then is the instantaneous rate of change in cost of a bolt of fabric per 1 yard of fabric. Right? So it's just your instantaneous rate of change for the cost of that bolt of fabric per change in length of the fabric. Cost in dollars, length in yards. I included in there. Is that okay? So derivative is an instantaneous rate of change of y per x. It's just writing it out, yep. In practical terms, what does it mean to say that f prime of 1,000 is 9? So 9 is going to be your change in cost per yard of fabrics, right? So we would say when 1,000, or when the length of fabric is 1,000 yards long, the cost to produce one more yard of fabric is $9. How many of us have econ now or past? Do you know what this is? This has an econ name. I know. Sam was like, what? This is your marginal cost. That's what this is. The derivative of a cost function is the marginal cost. It's the amount that it costs to produce one more unit at that level of production. Does that sound familiar, econers? Look at this, calculus all over the place in my real world here. It's all over my physics homework. It's all in my econ homework. Really anything that has rates of change going on, calculus is like all up in its business. I know. We're not going to do this example because it requires looking at some nasty graph, and I just don't want to bother with it. So we're done. This is the 2-7 homeworks. This will be due as part of Sunday's problem set. I wouldn't worry about starting any of it until I've just done the test. I worry about the test right now. What did you guys think on today? Was this okay? It'll take, it takes a minute to get your head wrapped around it, right? Once you've got it, it's going to feel okay. It'll take, some of us, it's going to take some practice to get like, okay, I'm seeing the mechanics of what I'm doing here. I get what to do. And then it might take an additional little bit more time to like get a real feel for like conceptually what is this doing? Like, can I apply this context and talk about like what stuff means? But I think like working through some examples where it's, like wordy problems to talk about like what stuff means, I think helps as like a good starting point to kind of start building out some intuition. And if you don't like this product, like the algebra involved with like doing these derivatives, like having to muck through all these limits, that's gonna end real quick. Because what we start doing is like proving some shortcuts, where it's like instead of doing the limit to do our derivative, if it's this form, we can just do this. Or if it looks like this, we can just do this. Or if it looks like this, we can do this. And we learn all these little shortcuts to avoid having to do the limit anymore. That's coming. We still have one more lesson before we get to the start of that, and that's going to cover like 4 sections. But the bulk of next test is going to be like 2/3 of it is going to be like algebra, like symbol pushing, like using these derivative shortcuts to find derivatives for functions. So if you are like, I don't do well with the conceptual parts, I like to push symbols, I'm really good at that. We have that coming. So it's a little symbol pushing for the next test. And then we look at application. We build out our symbol pushing tools to the extent that we're going to. And then we look at application. And that takes us to the end of first semester, in all reality. And we start the reverse process of the derivative in second semester. So it's like, oh, if I've taken the derivative, how do I recover the original functions? And that's second semester. It's doing the same thing now with this new calculus operation. So those are like the 3 pillars of AP calculus. AP is limit, derivative, and then integral is the backwards, the recovery function of the derivative. And that's the course, guys. You know. How's life? You guys seem really beat down today. Not usually as peppy as you are. Now I know it's 8th hour, but it's like only one day.
This week is going to be so bad.
This week is going to be really bad.
Yeah.
Am I the main reason? No?
Not like
50%?
yeah.
So that's not quite the main, but like as close to not being the main
Pretty
and
solid.
still being the main reason as I can be.
Yeah. I know I did too, but I feel like because you got shoes.
Yes.
What time it's at? What is it? I don't know.